Okay, brilliant. Okay, guys, can everybody see that? Okay. Okay.
Yeah.
Yeah, brilliant. Okay, and can you hear me? Okay, as well. Yeah. So there's two. I've got two of you that are after joining now, on the live stream. I'll just wait a moment. There's three there now. So I'll just say hi. So I can see who's there. Okay, there's four, five. So I'll just say hi, guys. I'm in a knot here where all the leads and so on. Okay. Okay, Sheilan, I'll just get started here. Is that okay? Okay, brilliant. Okay, so I'll just conscious, yeah, your question. So I want to make sure that you're definitely there. Okay, right. So let's just keep in mind, yeah, that what we have, in the previous sections, I've sort of harped on about this, yeah, is that we have always got some population. Okay, so there's some population that we're interested in, right? And look, it could be anything at all, but more importantly, there's more than likely more than one variable that we're interested in. There's probably many variables that we're interested in, and try to I suppose, let's say, characterize the relationships between them variables. But let's just concentrate on one single variable, and let's say it's the spending behavior of Irish people over a typical weekend, and that's what we're trying to understand. Well, that particular population, and I always keep going back to this, that population, if we could ask that question to everybody in the population, and we'd have a whole set of values, a whole set of spends, yeah, that people in Ireland have, let's say, spent over particular weekends. But more importantly, we can summarize that particular data set. We can summarize it down into specific values, yeah. So the population itself has an average, yeah, okay. It has an average mu, and it also has a variance, sigma squared. And if you want to look at the variance also from a standard deviation perspective, it has a standard deviation. Yeah, there's many there's many statistics, yeah, or there's many parameters, I should say. Yeah, there's many parameters associated with the population, associated uh, with the population. And just to list some off, it could be the mean that we're interested in, it could be the variance that we're interested in, it could be the standard deviation that we're interested in, it could be the skewness of the population that we're interested in, it could be the kurtosis, just different ways that we can summarize the population. It doesn't have to be them, it could be in regression models, it could be coefficients, in regression models, it could be correlations between variables. There's many different ways and many statistics or parameters that are associated with populations themselves. Yeah. Okay. But let's just concentrate on one of them, which is trying to understand the mean mu that's associated with a particular population. Okay. So let's just keep that in mind. Every population has a whole set of parameters that describes its distribution. Okay. And at this stage, we're just interested in the measure of center associated with that particular population, the mean value, and the mean is symbolized by the symbol mu. So how the hell are we going to get access to that particular value? Yeah. Now, typically, what we would do is we randomly sample. Yeah. So what we'll do is we'll randomly, yeah, we randomly sample from the population. Okay, which gives us a smaller data set. Okay, and with respect to this smaller data set, that smaller data set has a whole set of statistics this time is associated with it. It has its own measure. Hi, hi, Lakshmi. Sorry, guys.
We can't hear you.
No, you can't hear me. Okay, sorry. maybe what I should have done is I should have just gone straight into YouTube. Yeah, guys, is everybody on YouTube? Okay, can you? I've got 12 people listed on YouTube there. Yeah, can you just say hi if that's okay? But can you say hi through the YouTube chat? Is that okay? Okay. Okay, brilliant, brilliant, excellent, excellent. Okay, 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 that's great. Okay, so I have most of you there now. Okay, on the YouTube chat, so you can obviously hear me there. Brilliant. So I'm just going to run through the and my apologies for not being able to pronounce the names. Abdul Rahman, Sheilan, Valentina, uh, Dara, Karen, Vishal, Stelios, and Pallavi, Killy 89. Okay, so there's a fair 14 of you about there now at this stage. So let me just start this again, and then hopefully we can just get up to where we need to be, which is in relation to confidence intervals. And if you've just joined me, what I've been talking about is this, and what I always try to go back to is that we always have some particular population that we're interested in. Okay, so there's some population, and we're interested in understanding the characteristics associated with that population. Technically, what we say is that we're interested in understanding the distribution associated with the population. And there's many ways that we can define the distribution, and there's many parameters that define the distribution. Yeah, if that makes sense. Yeah, it's like a guy that goes out to get a suit. Yeah, for a wedding. There's many different parameters that the tailor is going to have to measure so that the suit actually fits the individual. Okay, so a population itself has many parameters associated with it. It has its usual measures of centers, the mean, the median, the mode. It has its measures of dispersion, the variances, the standard deviations, the range. It has measures of skewness and kurtosis. And depending on the many variables we're looking at and the relationships between them, there's different coefficients and there's correlations and so on and so forth. But the point I'm trying to make is this: is let's just concentrate on trying to understand the mean of a particular population. And we could understand it. Okay. So we could. Okay, so I can actually hear you guys there. So if you're asking a question, you're probably talking among you ourselves. Wait, I don't know how to mute that. So I mute that there. Let me just see here. Yeah, I'm just going to. That's grand. Yeah. So with respect to that population, what we're going to do is we're going to randomly sample from the population itself. And once we randomly sample, what we end up with characteristics associated with the sample statistics, things like X bar, things like S squared, things like S, and so on and so forth. X bar being the sample mean, okay? S squared being the sample variance, okay? S being the sample standard deviation, okay? Sample standard deviation, okay? And to be honest with you, in the real world, we wouldn't just take one sample, we would take lots of samples from the population. Okay? And effectively, what we're trying to build is if we take lots of samples, for each sample now we have an X bar. And from them, that collection of X bars, from that collection of means, we build the sampling distribution. Okay? The sampling distribution. And that sampling distribution is going to allow us to understand the population. Okay? But let's just once again keep it simple, and let's assume that what we've done is that we've randomly selected a single sample from the population, and what we have captured from that particular sample is we've measured its mean value, and we've also measured its variance stroke standard deviation. So we have X bar, and we also have S, and also, we also have N, the sample size. Okay. So the question now is this, is that from a variable perspective, okay, this is our variable, okay, the population itself, the population mean, okay, has to reside somewhere on this particular continuum, okay? It's either out here towards negative infinity, or it's out here towards positive infinity, or it's somewhere in between, yeah? because we're dealing with typically continuous variables. Okay, so what we can say for certain is that the real population mean, the real mean, must be somewhere on this continuum. Is that okay, guys? Okay. So how can this sample mean and this sample standard deviation stroke variance help us to pinpoint down where that population mean might reside? Okay, and the way we do that is we do that with confidence intervals. Yeah, and there's a particular formula for a confidence interval. Yeah, and I'll just write down the formula here. The formula looks like this: it's x bar, okay, minus t. I'll just say t. I won't make it any more complicated. Multiplied by s over the square root of n. And that's just a value this is, yeah? Okay. We know what x bar is because we've randomly sampled. We have our data, so we can calculate the mean. We know what s is. Once again, we have our sample data, so we can calculate the standard deviation. We know what the sample size is, n. So we've no problem in calculating this thing other than t. And I'll explain what t is now in a moment. T is just a scaling factor that's going to be associated with the size of the confidence interval that we want to build. But what we know, and I'm not doing the mathematical proof of this, yeah, but what we know is that this quantity here is a lower bound for the population mean. And then also the quantity x bar plus t times s over the square root of n, yeah, is an upper bound, right? So, Sheilan, what we're trying to do now is that we're trying to bound below and also bound above with two numbers. So we get a lower bound number, we get an upper bound number, okay? And what we'd like to be able to say with respect to them two numbers is that we have a certain amount of confidence that the real population mean, okay, will actually be between those two numbers, okay? So for example, if we want to build, it depends on how much confidence you want to have in this particular interval, yeah? Okay? But let's say for argument's sake that we want to build a 95% confidence interval, right? So let's say a 95% confidence interval. What the hell does that mean? All it means is that when we calculate the lower bound and when we calculate the upper bound, that we're 95% confident, okay? Here's the lower bound here, the lower. Here's the upper bound. That, excuse me, that we're 95% confident that the true population mean, mu, will be found within that interval, right? So we're 95% confident about that. But, excuse me, you have to be careful coughing nowadays, yeah? Right? It's a smoker's cough, I hope. So this 95% confidence interval that's demarcated by a lower and upper bound, what that says to us is that we'll have 95% confidence that the true population mean will be within that particular region, right? But with that said, we've got 5% of unaccounted for confidence, yeah, which makes perfect sense. So what the other 5% represents is that the population mean might not be in there. It might actually be above the upper bound, or it might actually be below the lower bound. Okay? We don't know where the hell it is. Yeah, and this is once again the thing about sort of when you roll a dice. Yeah, it's possible that you roll a dice and you never get a 6 for a very, very long time. Yeah. So it is possible that when we take a particular sample and that when we build this particular confidence interval with the lower bound and the upper bound, it is possible that the actual true population mean isn't in there and is actually outside of those particular bounds. Yeah. Okay? But what this particular theory allows us to do is that as we build up the evidence, as we increase the size of the sample, yeah, okay, what that allows us to do is to be, I suppose, I can't really say confident, yeah, is to be more sure, yeah, is that the population mean will actually be within the region that we've just specified. But we always have to keep in mind that it might not be there, it might be outside of that particular region. But the key thing is that when we build these confidence intervals, we can say with a certain level of confidence with respect to where we believe the population mean would reside. Right? And let me do an example on how to construct these things. Yeah. So let's say for argument's sake, right? So there's a little bit of work involved in this because we have to calculate. Well, let me calculate the mean and the standard deviation as well from fresh. Yeah. Okay. So let's say for argument's sake that we are interested We are interested in the spending behavior of Irish citizens, yeah, okay? Of students, yeah, okay? Let's keep that, okay? And we randomly sample, uh, let's say, keep it simple, let's say we randomly sample 5 students, okay? And ask how much do they spend? Ask how much do they typically spend? Okay. And what we got was something like this. So this is how much they typically spend over the weekend. The first person says, let's say, 75 euros. The next person said 62. The next person said 83. The next person said 105. The next person says, let's say, 40, just for argument's sake. Okay. So this is our sample. Okay. That's all we have sight of. And what we need to do is we need to calculate the sample's characteristics. So we need to calculate the sample mean, we need to calculate the sample standard deviation, and we need to calculate the sample size. The size is straightforward. It's simply equal to 5. Okay. The mean is relatively straightforward. It's the sum of those values divided by how many observations there are. So it's 75 plus 62 plus 83 plus 105 plus 40. Okay. And when I divide that, so that's equal to 365. And when I divide that by 5, I get a mean value of 73. Okay. So what we know is that the average spend of this particular sample is 73 euros. And there was 5 observations. So the question now that I have is, we need to calculate what standard deviation is. So let's have a look at the standard deviation. So I'm just going to construct a table here. I'm going to list these values down. These are my X values, my observations, 75, 62, 83, 105, and 40. And what I'm going to do is I'm going to calculate the standard deviation for these. And the standard deviation is the square root of the sum of squares all over the sample size minus 1. Let me maybe write that down here. So it's the square root of the sum of squares, the x minus the x bar squared, all over n minus 1. And that's equal to s, the standard deviation. Right? So that's what we need to calculate. So what I'm going to do is I'm going to calculate here x minus x bar squared for each one of those observations. Then I'm going to sum up this column to give me this summation of the x minus the x bar squared values. Okay? So I'll do this on the calculator. So the mean is 73. So the first observation is 75. 75 minus 73 gives me 2. Okay? The 2 squared gives me 4. Okay? The next one is 62. 62 minus 73 is going to give us 11, and 11 squared is going to give us 121. Then we have 83. 83 minus 73. The previous one was negative, but the square of it is actually going to give us positive. Yeah. Okay. We have 83 minus 73 gives us 10. 10 squared gives us 100. We have 105 minus 73 gives us a value of 32. And when we square that, we get a value of 1,024. And then we have 40 minus 73 gives us minus 33. 33 squared gives us a value of 1,089. Right? So the sum of squares here is 1,089 plus 1,024 plus 100 plus 121 plus 4 gives us a value of 2,338. That is my sum of squares. Yeah. Okay. So that is the sum of the x minus the x bar squareds. So what I now have is my standard deviation is going to be that summation, 2,338, divided by the sample size, which is 5 minus 1, and it's the square root of that. So I'll just do that in one go. So what we end up with is the square root of 2,338 divided by 4 gives us a value of, it's approximately 24. Let's keep these as whole numbers. Yeah, okay. So it's approximately equal to 24. So Sheilan, what I'm saying now is this, is I'm trying to understand a population in general, and in particular, I'm trying to understand the average spending behavior of that population. And what I've done is I've randomly selected from the population 5 observations randomly. And what I know with respect to that sample, I do know its characteristics. And its characteristics are that its average is 73 euros, its standard deviation is 24 euros, and the sample size was equal to 5. Okay. So what we'd like to do now is we'd like to use that information, yeah, okay, to put a lower bound and an upper bound around the true population mean. Okay, and as I said on the previous page, the formula looks like this: it's x bar minus t times s over the square root of n is less than mu, which is less than x bar plus t times s over the square root of n. Okay? So we have most of the stuff here. The only thing that we're missing is this t value here and this one over here. It's negative over here and it's positive over here. Okay? Now, what we know is this, is that the sample mean has a particular the distribution of the sample mean has a particular distribution associated with it. And actually it follows what's known as the student's t-distribution. Okay? So if we look at the t-distribution itself, yeah, the question that we're asking is, can we find a lower t value, a critical value, and an upper t value, a critical value, that has 95% of the area? Because I want to build a 95% confidence interval. I should have actually said that. So let's construct a 95% confidence interval. Okay, confidence interval. And the most important thing to go with this statement is construct a 95% confidence interval for the true population mean value. Okay, okay. So depending on the size of the interval, it doesn't have to be 95%. If you want to be more confident, you can construct a 98% one, a 99% one, a 99.9999% one. Okay, and we'll have a look at that in a moment, what actually happens to the interval, the way the intervals change in size when you put more confidence in or when you reduce your confidence. Yeah, but at every confidence level, there's a specific t value that's associated with it. Okay, so what we're going to do is this, is because the x bar is distributed based on a t distribution, we're going to look at the t distribution itself. Okay? And what I want to do is, so this is the t distribution for our true for the sampling distribution, and the true population mean is somewhere along here as well. Okay? So what we're going to do now is this, is that we're going to try to find a lower bound and an upper bound such that the area between them, okay, is 95% effectively. Okay? So if the area between these, and this is a symmetrical distribution, if the area between these two values has to be 95%, that means 2.5% of the area is in that tail, and 2.5 of the leftover area must be in that tail. Okay? Now, we've got a set of tables that allows us to figure out these critical values here and here. Okay? For the t-distribution tables, okay, I'm assuming you're working on the blue book. It could be the red one, but whichever one you're using, I'll just use the blue one here for the moment. Yeah, okay. And I'm just going to go to page on here. It's page 22. And what we effectively have is we have, where am I going to? We have, this is for the student's t-distribution. Okay. And the way this is set up is the tables have a leading row and a number of columns. Okay. So the leading row here is the area you've placed in your right-hand tail. Okay? Okay? Now, because we're building a 95% confidence interval, I'm going to have 2.5% in my right-hand tail and 2.5% in my left-hand tail. So the area in my right-hand tail is 0.025. Okay? And then what we have is listed down here is the degrees of freedom associated with this particular distribution. The degrees of freedom is based off the sample size, okay, and more importantly, how we actually calculate the standard deviation, which is n-1. Okay, so our sample is of size 5, so n-1, the degrees of freedom is n-1 is going to be 4. So if I triangulate in here, what I end up with getting is, you can't really see that, I'm sure, because it's very small, but I'm under the column that has p is equal to 0.025. And I'm coming down to the row which has degrees of freedom 4, and I get 2.776. 2.776. So effectively what that's saying is this, is that with respect to t values, okay, that the t value of 2.776 and the symmetry minus 2.776, okay, that there's 95% of the area between those two values. Okay. Now, what we're going to do is we're going to use those two values in here. The negative one here Now, we actually just put in the positive value, okay, because the negative sign here is capturing this negative value here, okay? So we put in this value here in here, which becomes minus 2.776, and we put it in here, which becomes plus 2.776. So in this situation here, what we have effectively constructed is something like this. Let me write this down again. So a 95% CI, confidence interval, right, in this scenario. As I said, it's x bar minus t times s over the square root of n is less than mu, is less than x bar plus t times s over the square root of n. It now becomes 73 minus 2.776 times s, which is 24, which needs to be divided by the square root of 5. Okay, that must be less than mu, which must be less than, well, x bar is 73 plus 2.776 times 24 over the square root of 5. Okay? You can see that this is a common factor over here. So let's just actually do that, okay, or a common term. So I'm just going to calculate 2.776 times 24, and I'm dividing that by the square root of 5, which gives me a value of 29.79. So it gives me a value of, I'll just put it into one decimal place, about 29.8. So this now becomes 73 minus 29.8 must be less than mu, which must be less than 73 plus 29.8. Okay? So over here, when I got 73 minus 29.8, that gives me a value of 43.2, must be less than mu, which must be less than, and over here, we end up with a value of 73 plus 29.8 is going to give us a value of 102.8. Okay? So a bit of work there. To be honest with you, the hard part is probably calculating the standard deviation. Yeah. Okay. Conceptually, there's a little bit more going on under the hood, of course. Okay. But effectively, what we've now created is that we've now put a lower bound and an upper bound on the spending behavior of this particular population. Okay. So let me just draw that here. Okay. So now what we have is this is 43.2. And this up here, okay, is 102.8. So what I'm saying is this, is that with respect to the population that this sample has been drawn from, okay, that I would be 95% confidence that the actual spending behavior of that population is between 43 euros and 20 cents and 102 euros and 8 cents. And I'd be 95% confident in that statement. Okay? But I might be wrong. Yeah, that's the key thing behind it. Yeah, I might be wrong, but I'll only be wrong 5% of the time, if that makes sense. Yeah. Now, it could be the case that I'm wrong on my first go. Okay? But who knows? Yeah. But what this is allowing us to do is just allowing us to place a confidence interval around the true population mean, but also to accept that, albeit we're saying that we're confident that the true population mean resides within that particular interval, we actually might be wrong and actually might reside outside of that particular interval. Okay. Sheilan, actually, had I got questions there? I couldn't hear if I had both Teams and YouTube open. So everything is good here. Not working for me. Okay. Sheilan, does that help? This is just the first thing. I'm going to construct another one, yeah, just to show you actually what happens in the real world, yeah. Right? And this is I think really nice, yeah. So what I'm going to do is, instead of me wanting to be 95% confident, yeah, I want to be 98% confident, yeah. So I want to be 98% confident. In other words, I want to construct a 98% confidence interval, yeah. So with respect to a 98% confidence interval, we calculate the t-value that goes into this formula. And once again, we have our t-distribution. So I want to be 98% confident, which means I want to find a lower bound and an upper bound that has 98% of the area in between those two values, which means I must be 1% over here and 1% over here. Right? When I look up the t-tables, the area that I have placed in the right-hand tail is 1%. So I'm going to go to 0.01. My degrees of freedom are still the same, they're 4. And now I get a different t-value. This time, where did I put that? Okay. My t-value that goes along with a 98% interval is going to be So 0.01 is going to be 3.747. 3.747, okay? Which gives us, I'm just taking this formula again, x bar minus t over s over the square root of n is less than mu is less than x bar plus t times s over the square root of n. Filling in the details, okay? I'm not going to do that. I'm just going to do the calculation. So let me actually just calculate this. So it's 3.747 times s. S is 24, okay? Divided by the square root of 5, okay? So this factor here becomes 40.2. So now we have that the interval will be 73 minus 40.2 must be less than mu, which must be less than 73 plus 40.2. Okay, so I just skipped the plugging in the values and just actually did the calculation. Okay? So now we have it must be 73 minus 40.2 gives us a value of 32.8 is less than mu. And over here, then we have 40.2 gives us 110 point. Sorry, am I right there? That gives us 113.2. 113.2. Okay? So in relation to a 98% confidence interval, I'd be 98% confident that the true population mean would be between 32 euros and 80 cents and 113 euros and 2 cents. Yeah. Now let's plot that. 32 euros and 8 cents is less than 43 euros. There you go. Okay, that's 42 and 80 cents. And 114 euros is bigger than 102 euros. That's over here. That's 114 euros and 2. The red one is 98% confidence. The blue interval is 95% confidence. Okay. Now, I think the important thing to take away is this particular fact, yeah, okay, is that what we can actually see is this, is that when I'm less confident, okay, the interval is a lot smaller, okay, than when I'm more confident, yeah, okay? And the thing is this is actually, I suppose, from this is, I suppose, let's say, that measurement problem, yeah, okay, which you've probably heard of in physics, yeah, okay. So the Heisenberg uncertainty principle, yeah, in relation to particles, yeah, that if you want to know a particle's position, you can know its position, but what you trade off is understanding on its momentum. If you want to understand a particle's momentum, you can understand it, but what you trade off on is knowing actually where the particle is actually positioned, yeah. Okay? So there's this trade-off, and this is a classic example of it, yeah. Okay? Is that if I want to be more confident in relation to where the population mean resides, yeah, well then my interval increases. Okay. See, this is like, let me get another pen here. This is like a classroom, yeah, okay? A classroom that's walled on the left and the right hand side, okay? And all the students are in that classroom. And Sheilan, I'm looking for you in the classroom effectively, yeah? Okay? So once again, if I tell people to concentrate down the first couple of, let's say, so I'm sort of looking up into the classroom, into the theater here, and these are seat positions. And if I ask people to concentrate in that seat within there, we know you're in the room, okay? Like the true population mean is in the room, yeah, okay? But it could be anywhere. Now, if I say to you to concentrate in a smaller interval, yeah, okay, well, you see, I'm trading off that you could be found in actually another area of the room that's actually quite large, yeah, okay? But if I increase the interval, yeah, well, you're more than likely going to be in that part of the interval, yeah. That's why my confidence is increased, yeah. There's less chance of you being in here, a smaller part of the room, if that analogy makes sense, and it probably doesn't. Just doing it here on the paper, yeah. When you're in a theater, yeah, it's sort of, you can visualize really what's going on. But the point being this is that if you want to be more confident in relation to the true population mean, you can be more confident in relation to it. But what you I suppose, let's say, what you sacrifice is the location. In other words, my interval is actually after grown in size, yeah. Okay. But because it's grown in size, it's covered more of the place where the population mean could be, and hence I've got more confidence that it could actually be in there. Okay? If that makes sense. Sheilan, have you? Is there any questions? Now,
That was really helpful.
okay. So brilliant. Yeah, I think the important thing is this, and look, Amir, I do totally accept. Yeah, is that I think for the vast majority of this particular class, and like I mean, albeit it's a H.Dip, is that people have been sort of out of class for a very very long time, and they've been out working, and now they're coming back, and they're encountering this stuff. I think the first thing is just to keep in mind is that the formulas, when you look at them, are very very complicated looking, yeah, and they're very scary, yeah. But they just boil down to multiplication, division, subtraction, and a little bit of addition, if that makes sense. Yeah. Okay. Conceptually, what's happening here is probably the more key piece, yeah, which is what I'm trying to reflect here in relation to the positioning that all these confidence intervals allow us to do is to put a lower bound and an upper bound on where we believe that the true population mean might reside. It doesn't mean it's in there. It just means it's more than likely going to be found in there, but it could be outside of them particular intervals. Yeah. And that's what all this theory is all about. Now, we don't have to just do confidence intervals for population means. We can build a confidence interval around, where's that page gone to? Let me go back here. Okay. Go back to the start. Okay. We can build a confidence interval around any population parameter. Okay. And the formulas just change a little bit. Excuse me. The formulas just change around a little bit. Yeah. The maths associated with how you get to the formulas is probably a little bit more complicated because you have to construct the sampling distribution of the particular parameter that you're looking at, or the statistic associated with that particular parameter. Yeah. But they're just the formulas. But we can actually do confidence interval for means. We can do a confidence interval for the population variance or standard deviation. You can do one for its skewness or its kurtosis and so on and so forth, if that makes sense. Yeah. I'm assuming that the only thing that he's done at this stage is a confidence interval for the population mean. Has he done any other confidence intervals? Anybody, any ideas? Has he looked at a confidence interval for a population proportion or anything like that at this stage? Okay, maybe he hasn't. Okay, that's okay. The other thing about this particular interval is that we're using the student's T-distribution. Okay, so I mean, things like in relation to the sample size, in relation to the standard deviation, you can see that we're using the sample standard deviation here. When we have the actual population standard deviation, we can use a Z distribution to actually calculate these particular bounds. The formula changes. The formula becomes X bar minus Z times sigma over the square root of n is less than mu is less than X bar plus Z times sigma over the square root of n. Now, the only two things have changed here, yeah? What I'm saying is this, is that even though we have our sample data, we could calculate the sample standard deviation from that particular data, yeah? But the sample standard deviation is only an estimate, albeit it's unbiased. It's still only an estimate of the population standard deviation. So imagine the situation where we actually know the population standard deviation. Well, if you know the population standard deviation, why don't we use that? That's a perfect estimate of itself, if that makes sense, yeah? So what we could do, but once we know the population standard deviation, the distribution changes to the standard normal distribution, yeah? And what we do is that we actually calculate the 95, the 90% intervals, and we actually calculate Z scores that go along with them, yeah? Which just uses the Z tables. But the same thing again is that you're looking for 95% of the area to be between certain values, or 90% depending on the size of the interval that was calculated. Okay. Okay. This video is actually being recorded here, so I have to download it off this and then upload it again onto YouTube. So it will be available later on this evening for you guys if you just want to reflect back over this. I think it's sort of coming up now to 6 o'clock. I do have another session later on, and I probably need to sort of get set up for that, unless there are any more questions, or there's anything that's a little bit muddy in relation to what I've done there. Right? Sorry, there's Karine. Do you mind to explain how to get the T-score again? I understood there are 1% for each side. Okay, so let's have a look at that again. So, and that's, I suppose, the key thing is that once you have the sample statistics, what we're really looking for, where do I put my pens? Here they are here. Okay. So once you have the sample statistics, you have X bar, you have S, and you have N, okay? The only thing that's required in the formula is that T value, okay? So it is the key piece in relation to the calculation. So X bar plus T times S over the square root of N. And once we know, because that's the only missing piece of information. So once we know that, we can actually calculate the lower bound and the upper bound, and it just boils back down to elementary arithmetic, if that makes sense. Yeah. Karine, it depends on the size of the confidence interval that you want to construct. Okay. So let me construct a different confidence interval. Okay. Let's say I want to construct a 90% confidence interval. Okay. Which effectively means I'd like to construct a lower bound and an upper bound, and that I'm 90% confident that the true population mean will reside between those two values. Okay? So what I need to do is I need to calculate the appropriate T value that's associated with a 90% confidence interval. So let's just draw that geometrically. Let's just draw our distribution. This is our T distribution. All the T scores are along here, and depending on the T score, there's a certain amount of area under the curve to the left-hand side or to the right-hand side of that T score. So what we're looking for is we're trying to find a lower bound and an upper bound so that 90% of the area is between those two bounds. Okay. So, Karine, this is the important point here. Yeah. If there's 90%, if we require 90% of the area to be between these two bounds, this is a symmetric distribution. So that means the tails must account for 10% of the area, which means 5% of the area must be in this tail over here, and 5% of the area must be in this tail over here. Okay. Now, we've got a set of T tables that allows us to calculate or to identify T values that have certain amount of areas to the right-hand side of them. And actually, we've set this up in relation to the T tables. It's the amount of the area in the right-hand tail. So we've placed, sorry, we've placed 5% of the area in the right-hand tail here. So I'm going to go to the T tables, and I'm going to go to the column that says 0.05. Right? Excuse me. And also what we have is we have our degrees of freedom, which in relation to a T distribution, okay, the degrees of freedom is equal to n minus 1. It's equal to the sample size minus 1. Okay, when we have a single sample that's being selected. Yeah. Okay? So n minus 1, our sample size in the previous example was 5. So 5 minus 1 gives us 4. That's our degrees of freedom. So now I'm going to look at the tables. On row 4, the row labeled 4, under the column 0.05. Excuse me, sorry guys. And what I end up with is, you can't really see them here. Maybe I'll just turn this light on here. I don't know whether that will help. Yeah, maybe it did, maybe it didn't. I'll go up a little bit closer. I have to come over here, I think. Yeah. So I'm coming under the column 0.05. Oh, there it is there. And I'm coming down to the row 4, which gives me, it seems like 2.132. So 2.132. So that's the T value that's going to plug in here, and it's going to plug in here, along with the X bar, the S and the N that you've already calculated. Yeah. Let's say I want to calculate, let's say, an 80% confidence interval. Well, once again, what we have now is, these are T values. We want 80% of the area to be between these two values. So if 80% of the area is between those two values, it means that the tails themselves must account for 10% each. Okay? That's the remaining 20%. So how much area is in my right-hand tail? In my right-hand tail, in my right-hand tail, there's 10%. So I'm going to go to the tables where we have 10% is 0.1, 4 degrees of freedom, and now I get the associated t-score that goes with 80% confidence. And in our case here, the t-score is 1.533. 1.533. Right? If I want to be, let's say, where am I going to? If I want to be 99% confident, 99% confident, okay, for argument's sake, that's how far our tables will allow us to go. Well, that means I want to have 99% of the area between these 2 points, okay? 99%, which means the tails must account for 1%, which means that 0.5% must be over here and 0.5% must be over here. Okay, 0.5% as a decimal is 0.005. So I'm going to go to the tables. I'm looking up how much area is in my right-hand tail. There's 0.05. My degrees of freedom in this example is 4. So I get a t-value. I get a t-value here of, if I'm not mistaken, 4.604. Okay, and that's the t-value now that I use to construct a 99% confidence interval. Okay. Sorry. I should have looked at that post there. Yeah, I'm just going to reflect back there for a moment. There was a post here by Korean who said, by Korean, the 3.747. Let me actually just find that number. The 3.747. Where is it gone? The 3.747. Yeah, okay. It is the t-value. Okay, and that's exactly what I've gone through there. Is for that particular t-value, we want 98% confidence, which means 1% is in both tails. In particular, 1% is in the right-hand tail. That's 1%. As a decimal is 0.01. The sample size is 5. The degrees of freedom is 4, which gives us 3.747. And that's the t-value that we use for a 98% confidence interval. Actually, guys, the thing about it is that them t-values don't change. Okay? So yeah, you can either just have in your mind a list of the t-values that go along with certain intervals. But the only thing is that if you don't know how to calculate them, if you change the interval size, yeah, it can cause a few problems, yeah. But there you go. I'm just going to reflect down through these chats here. When I use t-score and z-score, Tvalue, hi. When to use t-score and z-scores, okay? And I sort of mentioned that a moment ago. You'll be able to reflect back through this video because it is going to be recorded, yeah? Okay. So let me just go back here. Where is that gone to? I'm just going to try to find the sheet that I had a moment ago. Okay. Hi guys. What did I do? Did I throw it away? No. So just 1 second, please. So let me get rid of that. And there. Oh yeah, here it is. Here, yeah. Okay. Right. So the question once again is when to use T and when to use Z. Yeah. Okay. Now there's a few different rules here. Yeah. Okay. The T distribution is set up. The T distribution is a whole family of distributions. Yeah. It's a distribution that's associated with every single sample size. Okay. So it doesn't matter about the sample size when it comes to the T distribution. Yeah. Okay. You can go along and you can use it. You can use the T distribution in any case. And actually, all the modern statistical packages always give you back T values. Yeah. Okay. Now, the difference between these conceptually is that the T distribution, yeah, is we're using, well, this confidence interval here, yeah, okay, is the confidence interval for a population mean when we don't know the population standard deviation. In other words, and we estimate it using the unbiased estimate, which is the sample standard deviation. Okay, so that's the first thing. That's the first reason why we go for this one over this one here. When you do know the population standard deviation, okay, so when you do know that, let me just turn that off there. Okay. Oh, can that focus in there? Maybe I'll just try that again. Not to losing that. Right, guys, I'm sorry about that. Yeah, I'll tell you, there's just a camera there now, so the camera is after going a bit thing. It's getting in there now. Yeah. So let me just zoom. Let me just focus that a bit. Okay, there we go. Right. Brilliant. Okay, so when to use Z and when to use T? Well, clearly the difference between both formulas is that one has a sigma in it, a population standard deviation, and the other one has an S in it, a sample standard deviation. So the first rule is this, is that when you're given the population standard deviation, we'll go with the Z. When you're not given the population standard deviation, we'll go with the T. Does that make sense? Another rule of thumb is in relation to the sample size. Okay. Now, there are, and I can see that there's, let's see, Vishal. Hi. So, what happens if the sample size is 20 or more? Okay. Now, there's a thing called the central limit theorem that tells us as the sampling size increases, okay, that the sampling distribution, okay, associated with the sample mean tends to normality, okay, as the sample sizes increase, and when we take more and more samples of a larger and larger size, okay. So in that situation, yeah, okay, we can assume that the curve is normally distributed, yeah, okay, and in particular standard normally distributed, and we go with the Z, yeah, okay, when we have a large sample size, okay. Now, with that said, the question is, what's the demarcation point between large and small sample size? Now, most of the texts that you pull down off the shelf, okay, most of the texts that you pull down off the shelf would say that sample sizes of 20 or above are good, sample sizes of 30 or above are good. But what I'd be actually saying is this, is that, to be honest with you, there's other stuff that we're trading off against here, which is the power associated with the test, yeah? So it depends. It depends on the size of the effect that we're trying to measure. It depends on many different things. And actually, technically, every single test that we want to undertake, yeah, okay, that what we should do beforehand is what's known as a power analysis. And that power analysis will tell us the appropriate sample size that we should use to be able to achieve a certain level of power and confidence with respect to our experiment. Okay? And then you have the cutoff point. Okay? It might not be 20, it might not be 30, it could be 120. Yeah. Okay. But the cutoff point then would be that anything below it is a small sample and anything above it is a large sample, if that makes sense. Yeah. Okay. But typically, as the sample size increases, yeah, okay, we can go with the Z. And also when the population standard deviation is known. When we don't know the population standard deviation and we're going to estimate it, which with the unbiased estimate of S, well, then we can go with the T distribution. Okay, guys? I really do hope that helped you out. I'm just conscious of the time here now. Yeah, it is ticking away there, and I do have another session to try to get up and running. So maybe if there's any more questions, I think what I'll do is leave it there, and actually thank so many of you for joining it. It was 17, 18, it was around, I think it peaked around 20 actually at one stage. Yeah. Right? Is that okay, guys? I'm just going back over to Teams now to see whether there's anybody there that wants to ask any more questions. Yeah. Sheilan, is that okay for you? Pamela, was that helpful?
Yeah, that was really helpful. Thank you.
Okay, thanks, Sheilan. Yeah, okay. So will we go then? Will we continue at this particular time every Wednesday? What I'm going to do is I'm going to schedule another session now for next Wednesday. So hopefully tomorrow evening, when you're in class with Vladimir, you will have a better understanding in relation to what the alternative assessment is actually going to look like. And then what I'll do is I'll tailor supports specifically towards that. I am also conscious as well, Valentina, that you did ask the question in relation to probability in general, as in I think it was the addition rule and the multiplication rule, things like that. I think what I'll also do is I'll actually just set up a a live stream, or I might actually point you in relation to one of my sets of my playlists. Yeah, let me just think about that. So I will have to cover something on probability at some stage as well. Yeah, in relation to the foundational probability concepts. Okay, is that okay, guys? So can I end this now? Am I on mute?
Yes, thanks.
Okay, brilliant. Yeah. Okay, guys, thanks very much, okay, for joining in, and I'll talk to you soon. Okay, I'm just going to hit end on this now. And I'm going to hit end on the recording as well. So I'm going to just end the stream over here as well. So I'm going to end that stream, and I do want to end. Brilliant.